normal distribution. It's a very important distribution. It's actually a distribution that can represent a lot of real world phenomena. For example, for the researchers in healthcare, a lot of the measures in our body, like our weight, our height, our blood pressure, our cholesterol, like when they measure these factors in human body in a population, obviously each person is going to have a different value for those variables, but when they plot, for example, those a histogram of those variables for the population, they usually see that those variables have normal distribution. So for a lot of natural phenomena, those variables end up to have a normal distribution in terms of what are the possible values for those random variables, and what is the chance or frequency or probability associated with those values. Usually there is a average that has a higher chance of happening, and the numbers around the average have a higher chance of happening. And as we get further away from the average on each side, then the chance of happening gets lower and lower. And that's pretty much similar to the bell-shaped form that we have for normal distribution. And as I said, we always have an average, and we have also some spread around the average. Most of the, not all the times, the average and the numbers around the average, as you can see here, they have a higher density, higher chance of happening. But as you get further away from the average, getting to lower values or higher values compared to the average, the chance of happening gets less and less. So this distribution actually, as I said, is a very important applicable distribution and captures a lot of natural phenomena. For example, it's maybe some measure you guys do some measurements you do for water, for the soil, for the for, I don't know, give me some civil engineering examples. So those measurements usually follow a normal distribution. Natural phenomena usually follow a normal distribution. And for the normal distribution, like any other continuous random variable, has a probability density function, right? And this is the formula for the probability density function: 1 over sigma . Right. So this is the probability density function of the normal random variable, and the normal random variable usually goes from infinity to plus infinity. And like any other continuous random variable, if we want to calculate any probability associated with the normal random variable, for example, what is probability that x is less than 100? So we can look at the integral from minus infinity to 100 of this probability density function that we have. However, given as you can see, the probability density function is not a simple function. Calculating these integrals are not very trivial tasks. That's why the statisticians have transformed this normal distribution function to what we call a normal standard. Sorry, where's my curves? So they have transformed this every normal variable to what we call a normal standard random variable. And this normal standard random variable has average 0 and standard deviation of 1 or variance of 1. And when we put the average mu as 0, and we put the variance as 1, which means the standard deviation as 1, and we put these numbers in this formula. Obviously, the shape of this formula at the end is going to be a lot a lot simpler, and then calculating those integrals is going to be a lot easier. However, if we want to transform any normal random variable to a normal standard, random variable, which we also show with letter Z, then we have to deduct the average from that random variable and divide it by its standard deviation, and that gives us the equivalent value of the random variable in a normal standard distribution. So that way I can get any value for any variable that has normal distribution with a specific mu and with the specific mu and with the specific standard deviation, deduct the mu divided by standard deviation, and that gives me the value for the corresponding normal standard random variable. And then for the normal standard random variables, not only we can calculate the integral, but however, these integrals, the integral of this function after we put mu equal to 0 and sigma equal 1, these integrals have been calculated already, and they have the values of those integrals are already in a table. That's the Z table that you guys have looked at in the videos so far. And so those integrals have already been calculated. They are in those tables. So if you need to calculate any probability related to any normal random variable, all you need to do is to transform that normal random variable to a normal standard, and then find the value of the probabilities that you are interested in from that table, because that table already has the value of all these integrals in them. So you don't need to calculate anything, any integral again. Okay. So let's, all of you have the Z table available, right? So open the Z table. We are going to use that. So please open the Z table. It's in the folder for module 3. Please open the Z table. We are going to use that. And now I also want to look at one example. Okay. In this example, we have Chase Bank that is looking at the transaction amount of the customers. So the transaction amounts on the credit card of the customers, okay? And the dollar value associated with these transactions has normal distribution with average $250 and variance of $391, okay? So our random variable X is the transaction amount on credit card of the customers. Okay, for each transaction amount that we have on the credit card, this is the random variable X. Okay, the transaction amount of the credit card of the customers, and this random variable has been defined to have a normal distribution with average 250 and variance of 391. So X has normal distribution with average 250 and variance 391. Okay. And in part 1, what is the probability of transaction amount being between 250 to 300? So in part 1, what is the probability that the transaction amount is between 300 and is between 250 and 300. Okay. So if I want to find this probability, like what I said here, for any random variable that you have, if you want to find some probabilities associated with this random variable that has normal distribution with whatever mean and standard deviation, you first have to transform that into a corresponding Z variable. And to be able to do that, we have to deduct the mu of that random variable from it, and then divide it by its standard deviation. So we are going to do the same thing here. So to be able to find this probability, I have to, for x, deduct its mu, which is 250, and then divide it by its standard deviation, which is the square root of 391. And then if this inequality wants, I want obviously this inequality holds. So whatever I did to x, I have to do to the values on the right side and left side as well. So this is going to be 250 minus 250. And this is going to be 300 minus 250. Okay. And this is going to be, I'm sorry, equals to probability of, the left side is going to be 0 less than, what am I going to call this? For any random variable?
Z.
Exactly. If I deduct its mean from it and I divide it by its standard deviation, then that random variable is Z. And on the right side, I have 300 minus 250, 50 over square root of 391. And, okay. Can you tell me how I can rewrite this so that I can use the Z table value, given the fact that, as you have seen in the Z table, you see here, the values, you can pick the Z here. So here, you see, you can tell, in this table, you can tell, okay, what is your Z, as you can see here on the top, what is your Z? And then the numbers in the table tell you the probability of this, that your random variable is less than this value that you have in mind. So this is exactly the probability. This shaded area is what we see. Those probabilities are the ones that we see in the body of the table. Okay. So, however, here, as you can see, if it's Z distribution, what I want to find is the probability of between this number and some other number here. 50 over. So I want to find this probability. What is the probability that Z is between these two numbers? Okay. So if I want to be able to use the table to be able to find this probability, then the only way I can write this probability is to say, okay, this is equivalent to probability of Z less than 50 over square root of 391, which is Z less than this value, this whole area. Okay, which obviously is a lot more than the shaded red that I want. So but the table gives me the black area. If I give this value as the Z to the Z table, the table will give me the shaded black area as the probability of my random variable being less than this number. The table is going to give me that. So what should I do with that shaded black area to get the shaded red, which is what I need?
Minus probability
Subtract it.
Z less than 0.
Exactly. So minus probability of Z less than 0, which basically means, okay, get the black area first, which is the first part, and then deduct and then remove this green area from it. And this green area is probability of random variable being less than this value, which is 0. This is exactly what I have here. Just to be able to calculate the red area, I need to write this probability on the top into this form so that I can use the Z table to calculate the red area, which is what I want. Now, has anyone calculated this?
It's 2.53.
Okay, thank you. Z less than 2.53 minus probability of Z less than 0. Okay, so let's go to the Z table and find this probability. Z less than 2.53. Should I go to the top table or bottom table? I want to find this probability, Z less than 2.53. Top table or bottom table?
The bottom table.
The bottom table, because the Z values that we need, which are these numbers in this first column, are positive, but the numbers in the first column of the top table, they are all negative, okay, which are related to this part of the Z distribution. But the numbers at the bottom are related to Z, positive Z's, to this part of the distribution. But in any scenario, so the Z I have is 2.53, okay, 2.53. So 2.53, if I want to find the Z, I have to look at the first column, and then 2.5, that's Z equals to 2.5. And if I want to add the 0.03, I have to come to this column. When I add this to 2.5, then I have 2.53. So then if I go all the way right, and here if I come all the way down, then this value is the probability that I want, 0.994. Can you tell me what is this probability? Without even looking at the table. Did someone answer? So this is Z. Average 0, standard deviation of 1. And this is the probability density function, right? If I take integral of probability density function of any continuous random variable from wherever the random variable starts, let's say minus infinity, to wherever it ends, let's say plus infinity, what is the value of this integral? Always, always. You guys know that. For any continuous random variable, if you take integral of its probability density function over all possible values of that random variable, what is this value? Oops. No.
0.5.
Let me see, where did I go first? This value is not 0.5.
1.
It's 1. And that's the area under the PDF, under the probability density function. That area is always 1. And now you want probability of Z less than 0, which basically means, okay, take integral of the PDF, whatever it is, from minus infinity to 0. So take integral from minus infinity all the way to 0. This part. What do you think is that value? Given the fact that you know the whole area under the curve is 1. So this area is half of that area. So what do you expect that to be? 0.5. So if the whole area under this curve is 1, then if I need probability of z less than 0, when I look at this curve, this is exactly 0. And I need probability of z less than 0. That means area under the curve in here, which is less than the whole area under the curve, and the whole area under the curve is 1. So less than that, sorry, half of that is 0.5. Is that clear, guys? The fact that you don't answer means you.
That's clear.
Okay. So, however, you could also find that by just looking at the table as well. So if I want to find the probability of z less than 0 on the table, where should I look at? The lowercase z that I have to find in the table is 0. So on the column z, this is the 0 value. And it's basically 0.00. So the after decimal point is 0 as well. So I have to look at this column and this row. And this is the value I want, which is 0.5. Which we just talked about that even before without looking at the table, that value, if we know exactly what we are calculating, that value is 0.5 because it's just half of this area. So then if probability of z less than 0 is 0.5, then this probability that we need to calculate is this, which is 0.444. Right? 49, sorry. That's the probability. Okay. And okay, let's look at what is the part 2? What is the probability of more than 300 in transaction amount? Probability of more than 300 in transaction amount. The variable x that shows the transaction amount is greater than 300. Okay. We can go ahead and, as I said, like for every normal random variable, we have to first transform it into z. How do we do the transformation? First, deduct the mean, here 2050, divided by a standard deviation, and do the same thing on all the sides. So here is just one side, 300 minus 250, divided by square root of 391. And that's going to be probability of z, this whole thing, I'm going to call it as z, greater than, this is what we calculate, 2.53. Okay, so now I'm good. I transform whatever I had in x into z. I'm good. However, if I want to use the table that we have, the z standard table that we have, should I rewrite it in a different way to be able to use the z table?
Yes.
Well,
You could write it as 1 minus the probability z is less than 2.53.
53, exactly. That way, I can use the table because all the values in the table gives me this type of probability. For any z value that I'm going to find in the table, like 2.53 or any value, what table is going to give to me is probability of a random variable or z being less than this value. However, here I want a probability of z greater than something. So I cannot get this directly from the table. So I have to rewrite it as 1 minus probability of z less than this value, and then find this from the table replace it here, and find the total, the overall value of this probability at the end. Okay. So I need probability of z less than 2.53, which we already calculated on the top. 994, right? That's the probability that I calculated here. And 1 minus that is going to be 0.006 something. Okay, so that would be this probability that I want. Okay. Any questions so far? All good? Okay, then we also, okay, so this is the other question. Part 3 of this question also is important. So I want everyone to read part 3. It has a little more, you know everything you need to know to be able to solve this question, but I want to see if you guys can recognize what is this question asking and what is the setup of the question. So it says, okay, we are going to look at 10 customers' account independently. So customer 1, customer 2, customer 3, all the way to customer 10. We are going to look at each account independently. These accounts are independent from each other. And we see that all of these accounts have the same distributions in terms of the amount of transaction. So the amount of transaction of all these accounts has normal distribution with average 250 and variance of 391. Okay, this is the case for all these accounts. And these accounts are independent from each other, meaning that if this account has a transaction of $200 in the next transaction, that has nothing to do with this account, nothing to do with the other accounts, and so forth. So they are independent from each other in terms of their account, their transaction values. However, the transaction values in all of them follows the same distribution. Okay. Now it says that of these 10 customers that we look at, what is the probability that at least one of them, or just for now, forget about the at least. Let's put this aside. What is the probability that one of them has a exactly one of them has a transaction that exceeds 300? So the probability that exactly one customer has a transaction that exceeds $300. When I say what is the probability that exactly one customer has this condition, or what is the probability that two customers have this condition, what is the probability that all 10 of them have this condition? This thing that I'm trying to calculate here, the number of customers that have this condition, which can be either no customer, none of these 10, or 1, or 2, or 3, all the way to all 10 of them. That's the random variable that I'm looking at right now. And what do you think is the distribution? First of all, this random variable that shows number of customers that have a transaction greater than 300 among these 10 customers. The number of customers, possible values are 0 customer, 1 customer, 2 customer, all the way to 10 customers. Is that a discrete random variable or a continuous random variable? We are looking at number of customers.
It's discrete because it's countable.
Exactly. It's that this variable is discrete. We are right now looking at the discrete random variable. What is this discrete random variable? Number of customers that have a transaction greater than 300. And out of these 10 customers, how many number of customers that have a transaction greater than 300? So what are the possible values then for this random variable? What are the possible values for number of customers out of these 10 that we are looking at? Out of these 10 customers, what are the possible values for number of customers that have a transaction that exceeds 300? We are looking at 10 customers. How many of them can have a transaction that may have a value greater than 300? What are the possible values?
All 10.
One possibility. Oops, jeez. What happened? Okay, all of them is one possibility. What is other possibilities?
Yeah, none of them do.
None of them. None of them, one of them, two of them, three of them, all the way to all of them. Okay? So these are all the possible values that this random variable gets. If I'm looking at 10 customers, I'm looking at the transactions of each one of them. They are independent from each other. At the end, if I'm looking at how many of these customers has a transaction that is greater than 300, that's the random variable that I have. This is obviously a discrete random variable because I'm looking at number of customers. These are discrete values. I never have 2.3 customers. These are discrete values. And the possible values for number of customers out of these 10 customers that I'm looking at, number of customers that have a transaction greater than 300 are these 0, 1, all the way to 10, which means all of the customers have had transaction greater than 300. Now, what this question wants from me is that what is the probability that this random variable that I'm looking at gets value of 1? What is the probability that exactly one of those customers has a transaction value greater than 300? And let's assume for this random variable, I'm going to show it with y. I'm going to just use letter y to show this random variable. So this is what is the probability that y takes value of 1. The number of customers out of these 10 customers, the number of customers that has transaction value greater than 300 is 1. Okay, I want to calculate that. So does this discrete random variable remind you of any discrete distribution we have learned so far? Look at the setup of the problem.
Binomial.
Perfect. It's binomial distribution. So what is the experiment? Remember, for the binomial, first we wanted an experiment that we can repeat. What is the experiment, quote unquote, here? The experiment basically is whatever has happened with the person, looking at their transaction. That's basically the experiment in the binomial distribution definition. How many times I'm repeating that experiment? N?
10.
How many times?
10.
10 times for 10 different people, because checking the transactions of each person is like doing the experiment. And I'm going to repeat that for 10 people. N is 10. And what is the definition of success here? Remember, for each transaction, we wanted that transaction to be success or failure, and we defined what is success for us. What is the definition of success in this question?
They have over $300.
Exactly. The P, remember the P, which was the chance of success in a binomial random variable, here is the probability that the transaction amount of that person, which we show with X, is greater than $300. If a person has this thing, we call it, we define that, basically that's the chance of success for that. When we run that experiment, if we find this for a person, that the transaction is greater than 300, then we call that experiment to be a success. So here I want to see what is the probability that only one of the experiment, out of these 10 experiments, only one of them leads to a success. And the probability of success means having more than a transaction that is more than 300. So if I want to find the probability of success, I have to find this probability. Okay, so if I need to find the P, which is the probability of success, in binomial distribution, then I have to find this probability, because this is what I define as success in this setup. Probability of x greater than 300, we just calculated that was, if I'm not wrong, 0.006. So with that, if I want to find the probability that the random variable y, which is this discrete random variable that I defined here, takes the value of 1, which means exactly 1 out of those 1,000. So this is probability of exactly 1% out of those 10 people has a transaction amount that is greater than 300. Then I just write the formula of binomial. P, which is to the power of 1 minus P. To the power of 9 and 10 minus 1. Okay, so that would be the probability of exactly one of those 10 people has a transaction greater than 300. Okay, so, and if we go back to the original question, in the original question, it was, what is, if you look at here, it's the probability of at least one customer. It doesn't say exactly one customer. It says, what is the probability that at least one of these 10 customers has a transaction greater than 300? At least one. So how should I write then my probability? Yeah. Okay, so if I want to calculate the probability of at least one customer having a transaction greater than 300, how should I write? This is my random variable y that looks at the number of customers, right? That's my random variable y. But instead of exactly one customer, which we calculated here, I want to calculate probability of at least one customer has a transaction.
It's greater than or equal to?
Greater than or equal at least one, greater than or equal to 1 or 2. At least 1 means 1 is acceptable, right?
Yeah.
So it's greater than or equal to 1, right? Not 2. So at least 1 means 1 is acceptable, but anything greater than 1 is acceptable as well, so we are good. So now, if you want to calculate this probability, obviously when y has a binomial distribution, and these are all possible values for y, 0, 1, 2, 3, 4, all the way to 10, y greater than or equal to 1 means probability of y being to 2, or probability of y equals to 3, or 4, or 5, all the way to y equals to 10, which means a lot of probability for each one of them. For each one of these probabilities, we have to write something similar to this and calculate it. What is an easier way to rewrite this?
Rewrite it as 1 minus the probability of y less than or equal to 1.
Okay, as 1 minus probability of y. Should I put less than or equal to y, or just less than, equal to 1, or just less than 1? Sorry, in the here,
Yeah.
probability of y greater than or equal to 1 also includes probability of y equals to 1 plus equals to 2, 3, all the way to 10. So
So
then,
it should just be less than 1, not equal to.
exactly, if
Right.
equal to 1 is here, then it should not be here. So I have to write it as 1 minus probability of y less than 1, and sorry. And that is 1 minus. So probability of y less than 1, if these are all the possible values for y less than 1, then 0 is the only possible value. Less than 1 is the only possible value is 0, right? So that's basically 1 minus probability of y equals to 0. And probability of y equals to 0 is 0 out of 10 p to the power of 0, 1 minus p to the power of 10. So whatever that number is going to be, that is going to be your probability of at least one of those 10 customers has a transaction amount that is greater than 300. Okay. So this basically was a combination of both binomial and normal distribution. So basically the main random variable was binomial distribution, but to find the probability of success, the p for binomial random variable, then we had to look at the normal random variable and find that p or probability of success by doing some calculations on a normal random variable. And once we have the p or the probability of success here, this value, then everything else is just using the formula of binomial random variable, and we're good. Okay, so pay attention to that, read the problems carefully, and as you saw in this problem, you knew everything. You know all the things about binomial random variable, you know everything about normal random variable, so it's just a matter of reading the problem carefully and understanding what it wants from you, going back to the variables, knowing what is the definition, what you need to know about those random variables. For example, for binomial, you need to know n, you need to know p to be able to do any calculations. So when you read the problem statement, it's important for you guys to be able to understand that, okay, what is experiment here? Experiment basically is looking at each person, the transaction of each person. And that's what we call as experiment. What is the success in each experiment? Yeah, the success is if the transaction amount is greater than 300, right? So you have to know those variables very well so that you can find out, okay, in this setup, what is experiment, what is success, and what is n, and so forth, and then consequently you can do all the calculations.